Well, let us discuss the electromagnetic induction. Now, before starting to discuss about the electromagnetic induction, we essentially require to understand the knowledge we have learned in static charges and current electricity. That is, whenever there is charges at rest, we have electric field, and when charges in motion, that is in case of a current, we have magnetic field as well. In addition to the electric field, we have magnetic field. Now, in addition to that, we need to have the knowledge of Wester's discovery in 1820 that whenever you have a conductor carrying current, in that case, it will have magnetic field. The conductor will have magnetic field, and the magnetic field is concentric and perpendicular to the axis of the conductors, and the strength of the magnetic field is proportional to the magnitude of the current flowing in the conductor. Also, the magnetic field which you are getting, we can represent in dot and cross manner. That means if your magnetic field is coming out from your screen towards you, then we can always represent the magnetic field by giving a dot and circling it as shown. And if the magnetic field is getting into the screen from you, then we can represent the magnetic field by cross and circling. So these are some of the learning. Also, the subsequent learning in magnetic effect of current is that whenever you have a current carrying coil, it will be an equivalent bar magnet, being one side of the coil as north pole and other side as the south pole. Now let us discuss what is actually happening in case of inductions. What is induction? Induction is a phenomenon where you do not have a direct circuit connections. Look at the picture 1. If you see that we have picked up here one coil C1 and a bar magnet. In this case, north pole of the bar magnet is approaching towards the coil C1. Then the electromagnetic inductions phenomenon is such that the side of the coil which is towards the north pole, it opposes the changes. That means when the north pole is approaching, there is a change in magnetic flux on the coil of the C1, on the plane of the coil on the C1. So that process is being opposed. And how can it oppose the coil? How can it oppose the incoming of the approaching of the north pole? That it will develop a north pole which is towards the north pole of the bar magnet approaching. And that is possible whenever a current flows in the coil such that when you see the direction of the current standing on the magnet side, it will appear you as anticlockwise. If you are standing in the magnet side and looking to the coil C1, the direction of the coil should be anticlockwise, so that it will oppose. And when it is anticlockwise, you can always apply the right hand graph rule to see that the magnetic fields are ejected towards the north pole, and that pole being north pole, it opposes. So north pole opposes, so therefore that phenomenon is opposes. In the same way, if the north pole is receding away, so in that case also your current flows, but it is in opposite direction, such that the side of the coil which is vicinity towards the magnet side, it will develop south pole, so that it will as if oppose the going away of the magnet, and by developing a south pole in the vicinity of the magnet, north pole, south pole magnets. So how can it be possible? By developing a clockwise current. If you stand in the magnet side and look to the coil, you will see that the current should be such that it will have a clockwise current, and so that you can have a south pole which is vicinity towards the north pole as shown in the diagram. Now moreover, whenever the magnet is at rest, there is no development of current. That means when you bring the magnet towards the coil, there is a change in flux. When you take away the magnet from the coil, there is a change in flux. But during this change in flux times only, you are getting deflection in the galvanometers, and the deflection are opposite to the process. That is, when you are bringing the north pole, whatever the deflection is there, when you take away the north pole, the deflection is opposite, thereby confirming the direction of current is opposite in both the cases. In the same way, if you revolve the magnet, that means if you make the south pole approaching towards the coil, so in that case a south pole will be developed in the vicinity of the coil which is nearest to that of the magnet, that is south pole will be developed, and that is possible when you have a clockwise current. If you are standing and observing from magnet side, you will see that there is a clockwise current, then only you can have a south pole in the coil which is the magnet side. And if south pole is receding away, then in that case the current direction will be reverted, so to the deflection in the galvanometer, and there will be a development of north pole, and that is possible by seeing that current is anti-clockwise. If you are standing in the magnet side and observing that current will be anti-clockwise and the force is attractive. This thing we have represented in a tabular forms, and the concept we learned that the magnet can always be replaced by a current carrying coil. If we replace the magnet by a current carrying coil as seen in the picture, the same phenomenon will be observed. That means whenever there is change in magnetic flux with respect to time, there is change in magnetic flux, we develop a current, and that current is a induced current or induced EMF, so as to say, and that is the idea of electromagnetic inductions. And Joseph, your Henry, as well as your Michael Faraday, they independently make research over it, and finally Faraday has given a quantitative definitions how these magnetic flux can be measurables. That is why the discussion entirely owes to his name, that is Faraday's law of electromagnetic inductions. In the picture also we can replace these entire phenomena with a tapping key to confirm that whenever you tap the circuit for a switch on and switch off, during that switch on and switch off time, there is a change in magnetic flux, and during that small period of time, galvanometer will show deflection in the secondary coils. That means the confirmations of induced EMF or induced current, and when you tap key, you hold on or leave completely, then there will not be any deflection. So as far as the process of changing flux is there, the current flows. When there is the flux becomes constant, so in that case there is no current. This is actually what the electromagnetic induction to begin with in a qualitative manner, and the direction of this development of induced current is taken care of by Lenz's law, who gave a suggestive approach how the why the current is in which direction over to that of your Faraday's law, that it opposes, the Lenz's law says that the direction of induced current is such that it opposes the very cause of the phenomenon, and therefore whenever you have the north pole is approaching, there is a development of north pole towards the vicinity of north pole, and that is possible by Lenz's law. If you pick up the Lenz's law, it will confirm the direction of the current as we have seen, and the details of the quantitative discussions and more regarding structural problem solutions we will discuss subsequently. Thank you.